Okay, good afternoon. We have completed the discussion of the topic of gate dielectric. Right? We talked about some models of gate dielectric breakdown, some models about the defects in the dielectric, and some ideas, concepts of how to do accelerator testing, how to project the result from large capacitor test to long-term product reliability, and the concept of burn-in. We talked about some current research directions in both high K dielectric and the metal gate electrode. Okay, any questions about gate dielectric? Okay, if not, I thought I'll mention one other thing, which is really just something tacked on the end of the discussion of thin dielectric. It's a topic called non-volatile memory. All right, if you see your notes, I guess from lecture 25 last time, the last three pages from last time. It's called a non-volatile memory. All right. And without a lot of introduction about the relationship between non-volatile memory and thin dielectric, I'll just go ahead and tell you what non-volatile memory is, and I think you will see the connection why there's something that's often discussed in connection to thin dielectric. The diagram on the left-hand side is cross-section of the most common type of non-volatile memory, sometimes called a floating gate memory, floating gate non-volatile memory. Right? Sometimes you see the acronym NVM, that stands for non-volatile memory. All right? Just like DRAM is DRAM, this is NVM, is non-volatile memory. And the memory consists of a transistor, that is, you have a source, you have a drain, you have a substrate, you have a gate, and then between the gate and channel, supposedly there's only insulator, nothing else. Is that right? Now in this case, actually, the insulator sort of something's jammed in between, into the insulator, and that's called a floating gate. Now, floating gate is really just a piece of polysilicon that's not electrically connected to anything. It's surrounded by on all sides by a good insulator. You can consider that as SiO2. Sometimes there's some nitride involved, but totally surrounded by SiO2. And that's why it's called a floating gate. Totally floating. All right? So another way of thinking about floating gate is just a drastic way of introducing electron traps into the gate dielectric. So just visualize this whole thing as gate dielectric. In the middle, you insert a layer of electron traps. That really is one way of thinking about it, okay? Now, VT then depends on the electron charge stored on the floating gate, just like VT would depend on the number of electrons stored in these traps if this was a trap, right? Okay. Now, in reality, it's not just a trap, it's a piece of polysilicon. Now, why can polysilicon capture electron and keep them there like traps? In fact, better than any trap can. Well, to understand that, we'll just look at energy band diagram. Forget about a bias here. Even without a bias, you can see what I'm trying to do here is this may be the substrate. All right? This is the SiO2. This is the floating gate. You see, floating gate itself is a piece of semiconductor, right? That's why it has a conduction band edge, has a valence band edge, right? Right? So if you just look at that, almost like an MOS capacitor. However, this piece of silicon is not connected to anything. On the other side of this piece of floating gate is another SiO2, right? To the left-hand side of this other piece of SiO2 is our real gate electrode, okay? Sometimes called a control gate to differentiate from floating gate, control gate and floating gate, all right? So this is the floating gate, this is the control gate, okay? Now, if you think of this whole thing as really dielectric, it's probably not difficult to see why floating gate serves the function as traps. You see, if any electron gets to the floating gate, can it easily come out of it? No, it won't. It will be surrounded on both sides, in fact, on all sides, by a 3.1 eV barrier. Is that right? That's why it's like a trap. You can think of this just as traps. Okay? But it's very efficient. Okay, and VT, of course, depends on the electron charge stored on this floating gate or in this trap. Is that right? Specifically, you probably remember, if we store a lot of electrons in this floating gate or trap, VT actually increases. Okay? One way to remember that is say electrons would, repel the electrons away from the inversion layer, make it harder for the inversion layer to be established. That's why VT is large. On the other hand, if there were no electrons here on the floating gate, or you can sometimes even put positive charge there, okay, then you can bring VT low. Is that right? So depending on the amount of electrons put there, you can change the VT. Now, ordinarily, we only needed two kind of VTs. For example, VT equal to 1 volt, VT larger than 5 volts. Just example would be two states to determine the digital information that you store on this bit of storage element. Okay. Now, okay, I'll stop at that. So I won't say this anymore. So maybe I'll just bring this piece of information in. The newer type of floating gate memories actually try to store more than 1 bit information per floating gate transistor. Guess how they would do that? They would do that by measuring the VT of this transistor, not just whether it's high or low, but divide this into maybe, let's say, 8 steps. That's what's needed to store 2 bits information, by the way. If you can store, I was wrong, I'm sorry, you don't need that. You need only 4 states. If you can store 4 states, and if your sense amplifier is sensitive enough to separate the VT, not just differentiate between high and low, but which of the 4 states is in, you can actually store 2 bits information. All right, this is already a commercially available technology, and several companies are selling these called multi-level non-volatile memories now. All right, okay. Now, okay. So the question then is, how do you put electron in and take electron out? But before we do that, let me just mention another thing. I said these are very stable traps because the barrier is very high. Do you know how long these electrons have to stay on these non-volatile memories, floating gates? The general expectation is that in order for memory to be called non-volatile memory, it should store data for 10 years. In other words, let's say you unplug your computer there, okay, for a long time, and 10 years later you plug it in. Well, the basic setup is still on the computer. The BIOS is still on the is still available. That's because it's stored in this non-volatile memory. It will still be there. Okay. Now, if you translate that to how many electrons can be allowed to leak out of the floating gate, it turns out to be something like 1 electron every 10 hours. And it's quite amazing how good this floating gate functions as a charge storage element. Okay. It's because SiO2 is a very good insulator. All right? The barrier is very high. The tunneling leakage is very low. So, okay, storage is all right, or we call that retention. It's fine. Maybe we can believe that electrons can stay in the floating gate for a long time. The question is, how do you put electrons into this floating gate? All right. You put the electrons into the floating gate by using something called hot electron injection. How do you do hot electron injection? You ground the source. You put high voltage on the drain. You also put a high voltage on the gate. All right, and these voltages are significantly higher than the typical operation voltage of a logic circuit. We call these programming voltages, significantly higher. Under that condition, because of the very large voltage on the drain, there's a lot of hot electrons created. Is that right? And you recall, one of the things hot electrons can do is then jump over this barrier and get into, they can flow across this thin oxide and get collected by the floating gate. All right? So this is how we program this memory. We use hot electron injection to program it. It's okay? Any questions about hot electron programming? All right. So from this picture, you can see what voltage you need to apply to the gate is fairly large positive voltage. You see we're applying fairly large positive voltage relative to the body, let's say, in order to create this favorable electric field in the oxide, mainly in this piece of oxide, to let the electron to drift into the floating gate. All right? Okay. So it requires high Vg and high Vd for the programming to occur. And in a way, it's a good thing, because this allows you to select which transistor to program when you have a large array of transistors. Now here I show you 4 identical transistors arranged in 2 rows and 2 columns. All right. Now in reality, of course, you often would have 1,000 of rows and columns, right, to get say 250 megabit of transistors. Certainly, lots of rows and columns. Here we just show 4 of them. All right, identical floating gate transistor cells, and the symbol is put a bar, you know, in between the gate and the channel, and that bar represents floating gate clearly. Now, for example, if I want to program the one that's red, program this one. All right, how do you select it? What you do, of course, you have to put a high voltage on the bit line so that drain voltage is high, right? These 2 on the right-hand side, they won't get programmed because drain voltage is not high, so there will be no hot carriers, right? Well, what about the transistor in the upper left corner? Its drain voltage is high. Just because drain voltage is high, do we have a lot of hot carriers? We won't until we also have gate voltage, is that right? If you don't have cold carriers, you won't have hot carriers, right? So the transistor in the upper left corner actually will not get programmed. Only this red one will get programmed if we put high voltage on the lower word line and ground the top word line. See that? Okay. So this is how we select when we program, right? Okay. Once we have programmed this red cell, when we want to read it, what you do is, you can imagine, this is what you do. All right. So what you do is going to apply, say 5 volt, usually we'll apply the VDD to this word line, the lower word line, and then use the sense amplifier to sense whether currents flow through this left bit line or not. If it flows through the bit line, that current must be flowing through the red cell, because only that has a potential of conducting current. This cell, for example, even though it's connected to the same bit line, cannot conduct any current, no matter whether VT is in the low state, 1 volt, high state larger than 5, because the top word line is grounded. We did not apply the VDD to this top word line. Yeah? That's how we read. So if we want to read whether this is at 1 volt or 5 volt, what we put VT is at 1 volt or larger than 5 volt, what we do is we ground all these other cells and only ground other word lines, only apply this 5 volt to the lower word line. Now maybe what's confusing is this crossing. Crossing does not mean there's a shorts, all right? So this bit line is not shorted to the word line. Okay, okay. So we just see whether any current flows through the bit line when only this lower word line receives VDD. If the bit line conducts current, that must mean this red cell is at low VT state. If the bit line does not conduct any current, this red cell must be at a high VT state. So that's how we read it. Okay? Yes?
So when you program, you have to, how do you know it's programmed? You have to wait a certain amount of time?
Very good. So all these novelty memory these days, we actually have a state machine included on chip, and so what we'll do is we'll apply a short pulse, typically about 1 microsecond, and then measure to see whether it's already successfully programmed. It has correctly programmed in there. If not, then we'll give it another 2 more pulses perhaps before making that measurement or verification, it's called, again. If it's verified, then that's in. If it's not verified, we'll give a few more pulses. And typically there's a limit of how many pulses you're willing to apply before the circuit just give up, saying it has died. This memory is no good. All right. So there's a reliability issue you can see. All right. Okay. Good. So the verification is an integral part of programming. Same thing. All right. So now you have C programming. You're seeing how this programmed information can be stored, and you have seen how we can read that information. Now what about erase? How do you then erase the information from this transistor, floating transistor? What we use is Fowler-Nordheim tunneling to erase. And specifically, we usually do this erase erase the floating gate from attract floating gate or remove the electron from the floating gate to the source. This is what we do. We will ground the gate. We usually flow the drain. All right? And we apply a large positive voltage to the source. If you apply a large positive voltage to the source, and if this gate dielectric is thin enough, that's why this topic is discussed with thin dielectric. If thin enough, and usually 100 angstroms thin enough, electrons actually tunnel from the floating gate across this gate dielectric into the source. So your stored electrons gets removed. You see what I'm saying? That's how you erase it. All right? Okay. Now in comparison, erasing is a more difficult operation than programming, actually. For one thing, it's very difficult for you to erase only one bit or one byte at a time. Imagine, if you put high voltage on the here I indicated a ground, I'm sorry. In reality, of course, this ground just means another node, right? They're just, you know. So how can you access the source of individual transistor? You cannot. So normally we just erase a large portion of the chip, if not the entire chip, at the same time, right? Because they share the same source. So we just apply the high voltage to the source at the same time and erase that entire chip, or erase at least a big portion of the chip. Sometimes we call it a page, a very large page. All right? And for this reason, this kind of memory is often called flash memory. All right? Flash meaning, well, maybe that's not necessarily the original meaning. I guess it is, actually. The flash was introduced to describe this idea. That is, you don't erase bit by bit or byte by byte. Instead, you just flash, erase a whole bunch of them. Right? And in a way, it's not necessarily something we prefer to do, because it's not very flexible in terms of the architecture, but it's something that we do right now. Okay? Turns out there's a reason we also cannot afford to erase this just truly bit by bit, byte by byte, even if we could, because Fowler-Nordheim tunneling is kind of slow. Because Fowler-Nordheim tunneling current is not as large as this hot electron injection current. Why is that the case? Well, because we cannot afford to use very thin dielectric. Right? You can say, you know, 2 lectures ago, or one last lecture, we said, as long as the oxide is thin, huge amount of current flows through it, right? Can even be larger than the current we can put through copper without violating some building code. That much current can flow through thin oxide. So how come here we say Fowler-Nordheim tunneling is very small? Why is that? That's because we also want 10-year retention, right? We want to keep the charge for 10 years. If this oxide is significantly thinner than, say, 190 angstrom or 90 angstrom, it's known that they just don't keep the charge in the floating gate long enough. See what I'm saying? Because keeping the charge and not let more than 1 electron leak per hour, per 10 hours, is very difficult. So we have to keep this oxide pretty thick. All right? As a result, the Fowler-Nordheim tunneling is not very fast. So typically it takes only microseconds to program, but milliseconds to erase. Right? Okay. Another thing that's difficult, I'll just sensitize this to you because we won't mention this again, is that when you erase this whole bunch, many thousands of cells at the same time, you better make sure they erase pretty uniformly. It will be quite troublesome if you know, one of them got erased into a depletion mode device. Right? Now it will be very difficult for you to do subsequent reading and writing. I won't get into the details because reading depends on the fact that even the low state is still larger than 0 volt. Okay, so if you erase some into negative VT, you're going to get into trouble. It's called the over-erase problem. All right. So today, when we talk about the non-volatile memory, mostly we talk about some kind of called a flash. And by the way, I maybe should mention what's besides flash, what else is there? Well, there's the UV EEPROM, for example. We can erase them by UV light, all right? Now, certainly flash today is the important type of non-volatile memory. So flash memory, this we call the gate oxide or tunnel oxide, is about 100 angstrom, maybe as thin as 80 angstrom, but really couldn't do that, all right? And I'll explain the problem for that is something called endurance or cycling life. And after this transistor gets program erased certain cycles, the cell no longer is good, and I'll tell you what that means. And typically, the cycle is about 100,000 cycle, and in fact, manufacturers often have very hard time meeting the specification. And but it's something that kind of as a result of competitive force in the market that everyone's trying to meet. All right, and the reason that after this transistor has been written and erased a certain number of cycles, no longer good, is called stress-induced leakage. First, let me tell you what happens after you erase and this for a certain number of cycles. The oxide just becomes leakier. When the oxide becomes leakier, two things can happen. One, you cannot keep the charge on for 10 years. Of course, that's bad. The other, you also have more of these over-erase type of problem. That is, a few cells have the oxide that are a lot leakier than other cells. And so during the erase, then those leakier cells quickly gets erased into negative VT, for example, and cause problem. You know? All right, why does the oxide become leakier after stress? Well, you should be able to answer the question based on the discussion in the last 2 hours. You know, as a result of stressing, by the way, program erases stress, right? With high voltage across the oxide, send electrons through and then pull electron back out, right? That's called stress. After that, what will happen? Traps will be created in the oxide. Is that right? And when traps are created in the oxide, what will it do? It will make the oxide leakier. Is that right? Okay. We think that's what's happening, and that's called stress-induced leakage. Now, for example, if you look at the leakage, IV curve. All right. Let's say, well, this is not my hand drawing, but all right. The idea is that the bottom line is the initial Fowler-Nordheim curve. Let's say, all right. Remember, a Fowler-Nordheim curve should not be a straight line on a log I versus V plot, right? So the bottom one is the initial. Okay. As you do more and more stress, just get leakier and leakier. Can even look like that, right? This is called stress-induced leakage. Okay. All right. All right. Now, why does thicker oxide help? In fact, you can even argue, you know, thicker oxide is even worse. Because if you want to erase electrons from the floating gate across the thicker oxide, what do you have to do? You have to apply even larger voltage. Is that right? That's actually more stress. Why is that lower stress? And besides, the number of electrons that pass through this oxide also is fixed. Doesn't matter whether your oxide is thin or thick. And you can probably think, in fact, okay. Well, it turns out there's a very clever, very interesting reason why we have difficulty scaling below 100 angstrom in this case. The fact is, you see, if we have an oxide that's thick, let's say this is 100 angstrom or more, suppose it's 100 angstrom or more, right? The question is, a trap is created, where will it be created? If the trap is created very close to one electrode, all right? Yeah, electron will tunnel from the cathode into the trap very, very easily, but what will happen after that? Can electron get out of the trap easily? It cannot. So that's not too much of a problem, actually. For example, retention-wise, it's not going to serve as a stepping stone to keep leaking charge away. Yeah? If the trap is generated near this side, that's no problem because it's hard for the electron to go from the cathode to the trap in the first place. Right? So it's when we get into, you know, 70 angstrom, 60 angstrom, 50 angstrom, then the trap somewhere in the middle is close enough to both electrodes. Now we're in trouble. You see that? Okay? So for the thick oxide, you're only in trouble when you have two traps that happen to line up, physically lined up. Now you're in trouble, right? Yes? This is known as weak bits. In other words, when this happens, it usually doesn't happen throughout the transistor, the array. If you have, say, 64 megabit of a transistor, usually, a few dozens of them will fail first. So it's totally probabilistic. A cell where you just happen to have two of the traps lining up physically. Now those will become the ones that will give trouble, right? Most of the others probably does have one trap somewhere, but the one trap will either be on this end or will be on this end and doesn't hurt. If it's right in the middle, it doesn't help either. Why? Because we chose thick enough. So the one in the middle doesn't bother us either. But when we have two of them lined up, or three, that's a big problem. You see that? So one problem, difficulty dealing with flash memory is that its failure is so difficult to predict. It depends on such subtle mechanisms. How do you test for it? How do you test reliability? Can you afford to actually test every transistor 100,000 times? The answer is no. Time just takes too long. I already told you it takes 1 millisecond, 10 milliseconds to erase. Just imagine erase it this many times will take way too long. All right? So cannot test it. So what do you do? It's very difficult to do that. Okay? So if you create a trap traps in the oxide, what you see some transient current in the oxide. That's just the current due to filling the traps. And today's ammeters are so sensitive, we can actually measure the current that's the result of electron flowing from the cathode into the trap. It's a transient current. All right? But if we have a thin oxide like this, we'll get a continuous current, and that will cause the charge to leak. Okay? And the one problem with the flash memory is people are very concerned about the future for scaling. It has done very well so far, but the funny thing is, people have been using this thickness for flash memories, tunnel oxide, 100 angstrom. Okay, they start using this in the, let's say, in the certainly I would say the late 70s. Okay, so it's almost more than 20 years now. When this first used, this 100 angstrom oxide first used for the non-volatile memories, was considered really daring, because do you know what is the logic transistor gate oxide at that time? It's probably something like 500 angstrom. All right? Now, the logic transistor uses 20 angstrom. And guess how thick does the non-volatile memories gate oxide stay at? Stays at 100 angstrom. So this is not very good for scaling. Right? It's hard to design short channel transistor with the thick oxide, and takes high voltage to do erase if the oxide is so thick. How can very thin oxide periphery transistors support high voltage? So it's very difficult. So far we just do that by designing high voltage modules to modify the logic technology and use thick oxide transistors to do the addressing, for example. And so people would like to look for some other ways to get around this. And there are many new ideas. I just mentioned one. It's called a ferroelectric. Other ideas would involve a magnetic change of property of a film, and yet others would involve some thermally induced phase change of film. So there's different ideas of looking for new non-volatile memory, but they're all exploratory. The closest to commercial product is ferroelectric memory that actually has some low-density memory on the market now. Other than that, floating gate still dominates. All right. So, all right. Ferroelectric memory. How does that work? What is ferroelectric memory? The idea of ferroelectric memory is a new material such as PZT. There are many different kinds with acronyms like SBT, and so PZT stands for lead, zirconium, titanium. It has a lead, zirconium, titanium, and oxide. All right, and it makes this kind of a lattice. It will have lead at the corner of a cube, more or less is a cube. Think of this as a cube, more or less. Have lead on the corners of this cube. You see that? All right? Yeah. And at the center of each face of the box of this cube is an oxygen atom. Okay? All right? If you can answer this question, then you understand what I mean, where this oxygen atom is. I said oxygen as the center of each box, all right? So if we have only this box, don't worry about the neighbor, just this box. How many oxygen atoms would there be if there's an oxygen at the center of each of the faces of the box? How many oxygen atoms are there on this box? 1, 2, 3, 4, 5, 6, right? 6 faces, okay? So now you understand where it is, okay? All right, so you know where the oxygen is, you know where lead is, okay? All right? Now finally, where is this zirconium or titanium? It's that black circle in the middle of this box. It's okay? All right. Now just think of this as a mechanical picture. Does this black ball like to stay in the middle of the box? You know, imagine that there's certain size to this oxygen atoms, all right? Okay, and also this is not exactly a cubic. Let me make this height a little bit larger, all right? This is a little bit larger than this dimension. How's that? Okay, this is a little bit smaller here, and it's a little bit larger there. Okay. All right, that's the case. That's fact. If you are that black ball, would you like to stay exactly in the center of this box? Is that where you have most room? You find most room? Or could it be actually slightly above that center plane or slightly below the center plane? You see, the fact is at the center plane there are 4 oxygen atoms, right? At the center plane. So if you go a little bit above that plane, a little bit lower than that plane, actually it's a lower energy state. And that's the mechanism for the memory. So this lattice has a memory. In other words, the zirconium or titanium can either be above or be below. Now electrically, how do you tell? What's the mechanism? What do you see that? One way to think about that is called a polarization. The fact is that titanium and zirconium is an ion. The rest of this lattice is another ion, all right? So it's really a dipole. One is positive, one is negative. So depending on whether this titanium ion is slightly, let's say titanium ion would be a negative ion. Metal ion tends to be negative, as you know, right? So if titanium is above the plane, you have this case, a dipole, right? Negative charges on top, positive charge on the bottom. If the titanium ion is in the lower half of the plane, then you have this dipole. Is that right? You following what I'm saying? Okay. Of course, this is just one lattice. In reality, a film is made of thousands of lattices. But the fact is that if you just tie them up, right, this is a one layer, one lattice, another lattice in the film would be this, another lattice in the film would be this, another lattice in the film would be this. You still have one charge on the top of the film, one layer of charge on the bottom of the film. Do you see that? No matter how thick the film is, you just have that number of charge. It's just like a capacitor storing that much charge. All right? Okay? Next, if you want to change the location, that's what, suppose that the ion was on the upper half of the plane. How can you move the lower half of the plane? Turns out a very short applied electric field, a pulse of electric voltage, can move, push this ion from the upper half, squeeze through the channel between the 4 oxygen atom into the lower half, and then will stay there happily. You can take that electric pulse away, will stay there for years. See what I'm saying? All right? You reverse the polarity, it will move from the lower half of the plane back to the top half of the plane. Gee, that looks very nice, okay? Now how we actually read it, turns out we usually don't read for this static charge. Okay, in principle you may be able to read it, but that's how we don't read that way. Instead, we read the reaction of this film in response to an applied voltage. Suppose we apply a voltage pulse, all right? And this voltage pulse does not flip the location of this ion. In other words, does not sort of reverse the polarization of this film. You know what I mean, right? The voltage we applied is of a polarity that simply enhances, reinforces where the ion already is. If we do that, turns out the current that we have to put on this capacitor is not a very large current. In other words, the dielectric constant of the film appears to be not huge. I mean, it's still larger than SiO2, but it's not so large as the other case. Let me show you the other case. If we now apply a voltage whose polarity will tend to flip this stored polarization. You see what I mean? Okay? Then what happens? Then we have applied a current to supply the new charge. Well, let's stop here. Okay? Such that we used to have a lot of negative charge on this, we now have to get a lot of positive charge on that. You see that? This turns out to be a large charge. In other words, the effective dielectric constant can be in the thousands. Okay? So this is one way to read which polarity it is in. In other words, we're sending let's say, a positive pulse, and if this does not cause a lot of current to flow in, then we know, the polarity we stored is already in this polarity. Let's say called polarity 1. If, as a result of sending in this pulse, we have to send in a lot of current, then we know the polarity that stored is polarity 2, not polarity 1. And that's how we read it, okay? So let me just quickly just show you how to implement this in a form like a DRAM. There are many ways to do this. This is implemented like a DRAM. You all know how DRAM works, right? DRAM somehow just read what charge is on the bit line, right? Sends that charge. So what we do is this. We'll turn on this select transistor. We're sending this charge, right? Sending this voltage pulse, right? Whatever charging current that flows through this capacitor, and the amount of charging current flows through it depends on the stored polarity. Remember? Right? Right? So it could be either a large pulse of current flows through it or a small pulse of current through it. But whichever of the two it is, the same current pulse will charge up this bit line, right? So we just sense whether we get a higher voltage or lower voltage. You see what I'm saying? Charge on bit line, then we can tell whether it's polarity 1 that's stored here, or polarization 1 that's stored here, or polarization 2 that's stored here. You follow that? Okay. And you can do this, and you can also be non-volatile, because if for some reason the power is lost, years later, you can still read it. It's still there. The way it left, the polarization is still there. You see what I'm saying? Okay, yeah.
So whenever you read it, you charge.
That's one architecture. Yes, the way I described to you, it might destroy that polarization. For example, if it's polarization 2, and the polarization 2 is reversed by the voltage you applied, then you lost that information. You have to refresh, send them in. That's one architecture. You can probably think of some architecture where this is not necessary. Can you think of one? So one way to do is this. You don't read it that way, because this itself is still pretty big capacitor anyway. Even though it's not 1,000, it actually has a dielectric constant about 100 or 200. All right. In fact, one problem we have is differentiate, the amount of charging curve. Okay. Anyway, let's see, it has 200 dielectric constant just regularly. All right. That's already pretty good as a regular DRAM capacitor. How about just using this as a regular DRAM, right? You do refresh, by the way. Okay. So when you read it, you do refresh. In this particular example, you still do refresh. But at least you don't have to repolarize this, or reverse polarization. That also is important, because, like anything, there's always reliability issue. And you do this many, many times. Does this somehow get fatigued? It doesn't work anymore. And there's evidence that can happen. So you want to avoid reversing this the polarization repeatedly every time you read the cells. You can read it as a regular DRAM if you wish. And then the remaining question is, how do you store it in a non-volatile manner? Well, you have to be given a signal. Perhaps the PC you have to push a chain saying save, or the circuit detect the voltage dropping. So using the last 1 millisecond left to store everything on this information, and you can do that just by applying a particular voltage. You can save that information. And let's say, and the other architecture where, for example, is non-destruct reading. The easiest thing to do, you would say, why don't I simply replace SiO2 gate dielectric in an MOS transistor with this film? Why don't we just do that? In principle, you can. And with the two polarization, your VT will be different. Turns out the problem is, if you just have any SiO2 in the system, all right, you have two dielectric film now, all right? You have two capacitors in series. One is this capacitor, one is a thin SiO2 film, let's say. Because the dielectric constant, this film is so large, most of the voltage will be dropped in that thin SiO2 film, not on this one, for example. So it's going to be hard time programming erase, but that's still sort of a dream. And maybe one of you will figure out a way how to make that work. A transistor for gate dielectric is ferroelectric film. That would be very nice. Okay, if you have tried that, it doesn't work very well. But in concept, probably can work. All right, so it's worthwhile doing that as a research topic. Okay. Yes? One more question. That's correct. It's not. It's not. Yeah. The piezoelectric, ferroelectric often goes hand in hand because they usually require quite a polarizable material, and so often go hand in hand.
So then, also, is there some kind of stress built in with the memory? Is it stress in the film?
That's one possible explanation for this problem of fatigue. If you do this many, many times, perhaps the thing will fail. So it's certainly a property we prefer not to have. Okay. All right. Other questions? Okay, great. So non-volatile memory. Okay, no questions. Now we have 1.5 lectures left, and I'd like to use the time to talk about BJT a little bit. All right, this course is not about BJT, but I always use save 1.5 lectures, talk a little bit about BJT just so that we know a little bit. Now this is a typical picture of BJT today. All right, if you look at that, unfortunately, oh by the way, unfortunately the shading such that you cannot read very well. Let me just tell you what it is then. This is a shallow, deep trench isolation. They're called deep trench as opposed to shallow trench. They tend to be deeper than the CMOS isolation trench, okay? And we have a substrate, then we have a epitaxial layer, all right? Of epitaxial layer, okay? To say within this trench is where one transistor looks. Let me just mention, this is another trench, oxide. It's a shallower trench, shallow, it's oxide. So all the dark areas are oxides, okay? There's some deeper oxide trench and shallower oxide trench, all right? Let me just quickly show you where the source emitter drain is, and then you can see the details. Well, it turns out this is the emitter, okay? M plus emitter here, okay? I probably should have add M plus here, emitter, if I can. Maybe I'll just do it this way, okay? There's the M plus emitter, all right? This M plus emitter. M plus emitter, okay? There's a very thin base, and then there's the lightly doped collector, then heavily doped subcollector to reduce the collector series resistance. All right? We need to make a contact to the collector, and we need to make a contact to the base. We need to make a contact to the emitter. Contact is where the old design takes most room, but in this current design, you can see how we make the transistor small. How do we make contact to the base first? We make contact to the base by connecting the base to a sort of a little bit poly P plus region. And P plus region is connected to a P plus polysilicon. And polysilicon sits on oxide. Okay? So that's how we make contact to the base. All right? And the emitter contact is made through this M plus poly. So right on top, and M plus poly can sit on top of the P plus silicon contact, separated by an oxide. Okay? And in fact, this M plus poly diffusion dopant comes from M plus poly. Okay? And this poly is often called part of the emitter. We call it a polysilicon emitter. All right? And so that's how a transistor are made very small. Okay. Another new thing that's happening, MOS is getting, bipolar transistor getting sort of less important every year. Right now, the stronghold is something called silicon germanium BJT. You probably know, something pioneered by IBM, and many companies also are following suit, and mostly used in high-frequency RF applications, because the FT of the BJT can still be higher than the MOS transistor. So right now we're at a very interesting point, probably near a cross point, that is, people can already design very good CMOS wireless product. Some companies dedicated to that technology only use CMOS design wireless product. Others still think BJT makes the design easier and work better, right? And some even still use some gallium arsenide chips. So there are different ways of several technology are used. But the type of BJT used in high frequency application, or use silicon germanium as the base. It's not pure silicon. And silicon germanium in particular is graded in such a way there's more germanium near the collector and less germanium near the silicon, so that the band gap is smaller near the collector, band gap is larger near the emitter. Do you see what we just did? We just drew here. As a result, we have a built-in drift field for the electrons, and that's what makes the speed of this transistor very high. All right? Okay. Just in case you recall from somewhere before that, we could do the same thing just by changing the doping gradient in the emitter, in the base, right? This is probably what you heard. This doesn't work. Okay, it doesn't work well for several reasons. I'll just give you one simple reason. The reason, in order to do this, you have to dope the emitter side of the base heavy and dope the collector side of the base light, right? Is that right? Yeah? Now, if you dope the one side of the base heavy, do you know heavy doping does something to the band gap as well? That's called band gap narrowing, right? So as we dope our base more and more heavily these days, because we are using thinner base and yet we want to reduce base resistance, as we dope very heavily, the heavy doping here is going to make the band gap, what? Narrower near the emitter. That's opposite what we need. You see that? Okay. All right. So silicon germanium does give us the silicon germanium BJT, sometimes called a silicon germanium heterojunction BJT. Does give the best performance today. All right? Okay. All right. The CMOS people still say that we'll beat them just by enough scaling, and that may still happen. But, for a while, there's always going to be some advantage from using the BJT. It's just that its application is probably going to become smaller, right? Okay. Let's say 2 gigahertz can be served by CMOS. Then we'll say, how about Sonnet? Go to higher frequency band, then we want BJT, right? So the application domain perhaps getting smaller, but it's probably always going to be something that silicon CMOS cannot do. And that's where BJT can play a role, where gallium arsenide and other technology will play a role, right? Okay. All right. Okay. The next few slides you actually don't have in the notes. I noticed was not included in the notes, probably because when I planned the beginning this course, I thought I wouldn't have time to discuss that. But today, when I look at it, I think with 1.5 lecture, we can say some more. So I added a thing. Just look at the screen if you can. All right. Just some general concept about BJT, particularly related to those which have a counterpart in CMOS that we have already seen. So this is kind of a sort of a CMOS engineer's short course on BJT. All right. Hopefully we just tag on. We already know from the CMOS discussion and see how BJT vary. Now, in CMOS we emphasize the concept. If you look at the speed, whether you call the gate delay or just the speed, just charge over current, right? Right? Charge is, we call it CV, is that right? Okay? But here we wanted to sort of differentiate a little bit more. The charge can be made of 2 parts. One is called intrinsic. One is called the something that has to do with the load, CL, with the VDD. In the case of MOS, we didn't go through this detail because we just called it C. Because, whether it's intrinsic or extrinsic, it's just all capacitor. What's junction capacitance, what's overlap capacitance, or it's the gate capacitance of the next state, or interconductor, it's just capacitance, right? Now, it turns out bipolar transistor is a little more complicated. Transistor capacitance has a lot of charge stored in the base, for example. Of course, you can call that capacitance. But it's also useful not to simply call it capacitance, separate it out. I'll tell you why in a minute. So there's some charge stored in the transistor itself. There are also some charge connected with the load, let's say. Suppose we separate this way. Is that right? All right? Mainly reason is because all the charge stored in the MOS transistor, even internally, is a linear function of VD. In other words, just capacitors. As I said, overlap capacitance, capacitance. So the capacitance charge stored always something multiplied by VDD. So we can call that C. But in the case of a bipolar transistor, if you think about it, for example, the charge stored in the base, is that proportional to V? No, it's proportional to some current, right? Right? If it's proportional, we proportional to current, not proportional to V. Do you see what I'm saying? Right? So that's why we want to separate it out. All right? Okay? But whether you separate it or not, you can then turn this into two terms. The Q inversion part over I, you call that transit time. Right? And the load part is still the CL VDD over I. Follow what I'm saying? The MOS transistor also have a transit time. We didn't particularly spell it out because it can easily be lumped into the C. Right? It's a C. This we cannot, because this thing is not proportional to VDD. So we cannot call C something called times VDD. We cannot. Right? So we just separate them out as a transit time. Okay? The transistor also, MOS also has a transit time. It's just that the intrinsic capacitance over I's are transit time. All right? Okay. The interesting thing is that this stored charge in the bipolar transistor to the first order is actually proportional to I, to the first order. So therefore, when you divide this stored charge over I, you get almost a constant. Okay? And that's different from a MOS transistor. All right? A MOS transistor, that thing, if you do anything, is more like that. It definitely doesn't stay constant, vary with VG, things like that, because it's a charge over I, right? Okay, you know what I mean. Okay, so next thing, with this two separate points, then we can make a plot. Tau versus load capacitance. Tau versus load capacitance. Clearly, tau is a linear function of load capacitance, right? Okay, the slope will be equal to VDD over I. Is that right? Let's assume VDD is fixed. The slope basically will be related to I in a tau versus C plot. Is that right? Okay. Well, this is a typical picture between MOS and BJT. All right. That is, BJT still conducts more current than the MOS transistor. Of course, MOS transistors are conducting more and more current as a result of scaling. And for the same reason, remember we said MOS transistor, we always want I to be very large in order to improve the speed, right? But bipolar transistor conducts even more current for a given micron square area of the silicon. So as a result, if you have a large load, bipolar transistor is very good relative to MOS transistor. Okay? What I'm saying? Yeah? And yet, when you have a very small load, MOS transistor is actually a faster device than bipolar transistor. Okay? That's why MOS transistor is actually very good, because bipolar transistor store a lot of charge. MOS, if you don't have much load, you don't have a lot of these charge there. Okay? Scaling issue, CMOS versus BJT was debated over a long time, but I think pretty much people concluded that scaling is favoring MOS. Both technology benefit from scaling, but CMOS benefit even more, and that's why over time BJT's domain has been reduced. Okay, so there's this technology called a BiCMOS, and that's one reason I guess to throw away this at the beginning of term. I'll take it away. This is a little bit out of date. Let's not worry about it. Today, when we say BiCMOS, we typically mean using the bipolar transistor for RF, let's say, and using CMOS for everything else. But If you have the bipolar transistor, you can also bipolar transistor as the buffer device in some logic circuit as well, some portion of logic circuit where you need to drive a long line, for example, of interconnect. You don't have to use a very large W CMOS transistor to drive it. You can use an MOS bipolar transistor to drive it, right? Because it's a large I, okay? And you can do that, and that circuit will look like this. Okay? This is an inverter, a bi-CMOS inverter. Basically, the line is driven by bipolar transistors. Since we only have NPN bipolar transistor, we don't have complementary, so you have to be a little bit complete way to drive two NPN transistors to end up with an inverter. Okay, so this is known as a bi-CMOS inverter. Okay, but it's not very big topic now, so I will not spend on that. Instead, let me go on to talk about some other things. The big thing about bipolar transistor, therefore, is speed, right? Because that's what we use it for, RF, right? We're going to go use it for 10 gigahertz, 20 gigahertz, 40 gigahertz. So what determines the speed, particularly for bipolar transistor? Well, you all know it has to do, textbook usually start with base transit time. And you may even remember it's proportional base width squared over 2 dB. Okay? This, by the way, assumes there's no drift field. With drift field, you can probably reduce this by a factor of 5, okay, which is very important, all right? But I just use this to remind you what we're talking about. What determines the speed of bipolar transistor is things like transit time, right? Okay. But this is only one part of the transit time. We introduced this concept of transit time, right? Tau TR earlier, two slides earlier. You can think of the transit time actually involves transit all the way from emitter to collector. If there's some charge stored in polysilicon, anywhere there's any charge stored, it will contribute to the transit time. Sure, there's charge stored in the base, but by making the base very thin, by building electric field in the base, well, the base transit time doesn't really dominate. I mean, it's still large, maybe 40–50%. But still, a lot of the time is spent even just flowing through the polysilicon in the single crystalline portion of the emitter. And of course, is the base. Okay, a base emitter junction also stores charge. All right, base emitter junction stores charge. All right. If you draw an energy band diagram, you can convince yourself there's actually more electrons stored in the higher electron density in the so-called depletion region between emitter base and in the base itself. Try to convince yourself of that. Draw an energy band diagram, all right? See where the Fermi level is relative to EC. Okay, here. We're looking at this diagram. We will have this energy band diagram, right? This is the base. Well, we're concerned about charge stored in the base, right? Right? Tell me, where do I have more electron density, here or here? In the depletion region, where do we have more electron density? Right? So when we change the bias, we're changing the electron concentration in the base. We're also changing electron concentration here. And there's more electrons. So, but fortunately, the width is narrow, right? That's what we're counting on. So this is not negligible. And then there's the base transit time, right? And then very importantly is the collect transit time. I want to emphasize that. Today, mostly we're going to talk about this. That's because we need a fairly thick collector. Why do we need a thick collector? If the N plus directly butt to this P base, the breakdown voltage of this bipolar transistor will be too low. Not only because we have heavy doped M junction and quite heavily doped P junction, which make the base collector junction breakdown voltage low, but also because of something we talked about in connection with snapback breakdown of MOS transistors. Do you remember what that is? Bipolar transistor has two breakdown voltages. The one that's lower, of course, truly limits us. And the lower one can be many times lower than the breakdown voltage of this junction, right? By the cubic root of beta, by that factor, for example. So if you want fairly decent breakdown voltage of the transistor, bipolar transistor, we better make this PN junction breakdown voltage quite large. Quite large. And how do you make a large PN junction, a breakdown voltage for PN junction? You insert a layer with light doping, right? Right? So for this reason, we have a fairly We have very thin emitter, with very thin base, we have a thick collector. So the transfer port times through that is actually quite significant, and in fact, that also becomes function of current. I'll get to that. So remember, this transit time going through collector is a problem, and we're going to talk about. I'm sorry, I maybe I should not overly emphasize that. Sorry about that. No, that's actually not what we're going to talk about. It's the base is what we're going to emphasize, but the base comes from the collector. Let me just go into that. Any question about this? If not, all right. So the question is, if you look at the data, we won't give you the explanation here. If you go to the data, well, first we look at the equation. Tau is equal to transit time all the way from emitter collector. Suppose we say to the first order is not function of current, then times VDDC over I. If you believe this, then you should be able to plot tau as function of current, right? We normally plot this log current because we're willing to explore wide range of current in order to find the sweet spot where the bipolar transistor is at its fastest. Okay, we're willing to burn a lot of power to get speed if necessary. All right. So suppose we do that. Theoretically, let's see. Do you agree? It should look like this. That is, as current increases, tau will decrease, right? Speed will increase. Is that right? Is that right? Until large enough current, then tau is saturates at transit time, right? Yes? Well, if that's the case, then you would say, gee, I just use the largest current I'm willing to burn, that's fine. But it's more complicated than that. What turns out, for some reason, the transit time actually increases at high current. All right? So the transistor is the fastest at some intermediate current. Put another way, if you plot the frequency, cutoff frequency peaks at some current. If you have low current, you cannot get the fastest out of the transistor. If it's too large current, you don't get it. It's only at a particular current. And this current actually can also be a function of, for example, VCC, depends on your bias, for example. All right? So we're going to talk about this phenomenon. This is the remaining thing. What determines the peak operation frequency of the transistor is this new phenomenon we have not talked about. The rising part is the result of this term. It's quite easy. All right? Any junction capacitance is anything you can describe as capacitance, VC as the charge is in here. All right? It doesn't have to be interconnect, by the way. It can be just the junction capacitance. All right? There will be plenty of those, of course. But what determines this? What makes the delay increase as current increase? We'll talk about that. And that is called, the answer is, what's the response for that? It's called a Kirk effect, also called base push-out, all right? And it happens at high currents. We call it a high current effect. Because of the Kirk effect, or because of this base push-out, the speed of the transistor drops when current increases. So we're going to describe how that happens. All right? Okay, just some interesting physics or so, even if you're not particularly curious about bipolar transistors. What determines its peak cutoff frequency is actually some interesting stuff just about the semiconductor. All right. The question is, all right, here the doping is not 10 to 18. Usually it's not that high. Maybe 10 to the 16s. I probably, what example did I use? I don't know, but I used the example. All right. Let's say maybe 10 to the 17s, let's say. Okay? This usually is not that large. Because we want the high breakdown voltage, right? Maybe 10 to 17s, maybe less than that, all right? A few 10 to the 16s. All right? That's typical doping. Okay. First, I want you to all have a concept. What current density is involved? This is the emitter, this is the base, there's a depletion region between the base and the collector. This is lightly doped collector, this is so-called subcollector, that buried layer. All right? And what current density, I mean, take the current divided by the cross-sectional area, right, of your emitter or of this, doesn't matter, okay, anywhere. Now, typically, we can conduct about 10 milliamp through a transistor maybe of 10 micron by 0.5 micron, and usually we refer to the size of the emitter, right, which is determining the cross section of this the current path. The current path is determined by the size. The size of the current path is determined by the size of the emitter. You can visualize that, right? Okay. And this is size emitter, okay? And in fact, we can even operate higher than this density. But if you do that, take my words for it, you end up with 200,000 ampere ampere per centimeter square. It's very high current density, all right? 200,000 ampere per centimeter square, all right? So here's the question. How can this lightly doped region carry that current? Now, we know it takes a large number of electrons to carry large current density, right? If the number of electrons not large, they just have to move at higher velocity. But velocity will be limited by saturation velocity. Is that right? Is that right? So let's see how much charge is needed in order to carry this current density. We'll put a Q here, we'll put N here, we'll put V set here, right? Saturation velocity. Current density is always equal to Q N V set. Is that right? Is that right? Yes? Yeah? Okay. And then, I don't know why I put it smaller, let's just say equal to, all right? Let's put it this way, okay? Just ask the question, what is needed? What N is needed, even if all of them move at saturation velocity, in order to carry this much current density? All right? Okay? All right? And we found out that's going to be 10 to the 17th. Okay? All right? Follow what I'm saying, right? And by the way, saturation velocity is something you can only attain at very high field, of course. So if you have doping a little less than that, or if you have current density larger than that, something quite dramatic will have to happen, because this equation no longer is satisfied. Is that right? Is that right? This inequality is no longer satisfied. Something quite dramatic, right? Saturation velocity cannot be larger than that. N cannot be larger than that. And yet, you're forcing so much current through the transistor. So what is happening here? Okay, so the answer to that is the whole key of this whole thing, Kirk effect. What's happened to that is this. It turns out there are two components of charge in this lightly doped base. All right. So let's concentrate on what happens in the lightly doped base. Let's just add this comment. In the lightly doped, not base. What did I say? In the lightly doped collector. Lightly doped collector. Okay. In that region that we think there may be a problem. In general, it does not have to be neutral. When we said that the current density, that when we, in the previous example, we were assuming that N has to be equal to ND. But that does not have to be the case, right? For example, we can inject a lot of electrons into the base. Why can those electrons not be injected into the collector? In the past, we never talked about injection of electrons into the collector because there's no need for it. But now there's a need. When you have so much current flowing through, they're going to carry electrons from the base into the collector. There's nothing wrong with that, all right? So N actually can be larger than ND. Does not have to be equal to that, all right? In fact, N will be determined by what's needed to carry this much current. So therefore, I should say Qn then will be equal to Jc over V set, such that the collector current can be finely carried by some N. It's just that the N is larger than ND, that's all. There's nothing wrong. N can be larger than ND. So that's the answer to the dilemma the previous slide introduced. All right? There's nothing wrong. The current, your circuit designer forced this much current flowing through it just by, pumping so much current into the base. Indeed, current will be flow through this collector. Jc will be that large. Saturation velocity cannot exceed, no problem. N just become larger than ND, that's all. Now, if N is larger than ND, we will have a net charge density. Why? QND is the density of ionized donors. That's positive charge. This is Qn, the negative charge density, right? The difference between the two is the net charge. So what's new is our lightly doped N region is no longer neutral. That's how it has to happen. It's no longer neutral. Specifically, it will be negatively charged, let's remember, all right? Because we have now more electrons than we have donor atoms. So this will be negatively charged. Now, before I show you more math, I want to show you some drawings. The first drawing I showed you is the usual depletion region sketch, okay? The usual depletion sketch, you know, what do we say? We say d dx is equal to charge density, right? Rho over epsilon, is that right? Right? d dx is equal to rho over epsilon, right? So in the normal case, because there's no j, that's the way we usually remember, no j, then d dx is equal to q and d, right? If you don't have any current, just the p-n junction depletion region analysis. d dx is equal to q times nd, is that right? With this particular sign of the d dx, we know E versus x looks like that. E decreases to 0, right? Yeah, peaks at the base and collector junction. I'm assuming this is a one-sided junction, heavily doped P, lightly doped N. So the electric field peaks at that P-N junction and drops to 0 somewhere. Is that right? Yeah? In fact, I should have preferred to drop this to 0 earlier than that so that, you know, so that you don't get confused. I'm not saying electric field drops to 0 at the buried field. It drops to 0 somewhere here, let's say, right? Right? Now, suppose when J happens to be equal to Q and dV set, namely rho is 0, you see, at a certain J, the rho can be 0, right? That's when J is equal to Q and dV set. This is not important, don't memorize this number. But I'm just saying, as we now start to pass current through it, at some point, d dx can be 0. Is that right? Is that right? In that case, the E versus X will look something like that. Is that right? The area between these two curves will be equal. Why? Because they are equal to the applied VBC. All right? Area under this electric field is equal to the voltage. Right? Since we fixed the bias VBC, so the area should be equal. All right? But shape will be different. This still does not hurt us. At this point, the transistor is still pretty fast. All right? Next will be problem. If J is even larger than that, if JC is even larger than Q and dV set, even larger than that, now d dx will reverse sign. Reverse sign meaning electric field will have to change in this direction, right? So I drew for you 3 different kinds of curves for 3 different slope. 3 different slope meaning 3 different JC. Increasing slope just meaning larger JC, right? One thing in common between the 3 curves is that area between the 3 must remain constant because that's VBC. Is that right? So as we increase J, you know what happens? What happens is now we have the so-called high field regions now become narrow, and there's a neutral region now next to the base. This is known as current-induced base, CIB, meaning current-induced base. Because in this region, we don't have a high field. They cannot be moving at saturation velocity, cannot be due to drift. They must be moving by diffusion in this portion. In that sense, it's now an extension of the base. The base used to be this wide. Now, under this condition, for example, base is this wide. All up to here is base, all carried by diffusion. You see that idea? All the voltage can only support this drift at saturation velocity in this portion. That's all it can support. If I have a larger VCB, of course, I can support larger length at the same slope. You see that? That's why if I have larger VCB, this cutoff frequency can peak at higher current. All right? So this concept is called base-induced, current-induced base, CIB. Is okay? All right. So you got all the base idea now. As current increases, base get wide. Now we all know the speed is proportional to the base width squared, right? Right? Number one, it's a very sensitive base width. And number two, the potential size of this current induced base many times larger than the actual base, because the slightly doped collector is much thicker than the real base. The base we try to make it very thin. The collector we try to make it thick so that we get large breakdown voltage, right? So when you put all this together, it should not be surprising that when current gets too large, speed certainly drops, right? And if I ask you next question, you probably should also have an answer. What would be the effect of this base push-out? By the way, this is why it's also called the base push-out. It's called the base push-out, called the base widening, called the Kirk effect. Can you see whether base widening would have an impact on beta, on current gain, just on the DC current gain? Can you see? Is there any impact? Just based on what you remember, what determines current gain? Base width, let's take that. As a result, do you expect current gain to become better or worse when base push-out happens? Become worse. That's true. So if you look at the gain of the transistor at the high current, it also drops. Okay, and we often describe that as due to the conductive modulation in the channel. That's true. But when this happens, you further drop. Okay, but to be honest, we're not as concerned about the gain drop. We're more concerned about speed drop, because we're really trying to get the highest possible speed of a transistor, bipolar transistor, right? So that's really what we talk about Kirk effect is that. The remainder, I really don't have to go through with it. I'll just tell you what it is. We don't have to go through it. And if you are curious, maybe you want to, all right, we will do that, okay? Why don't I do this? Let's just take 5 more minutes to go through a few equations, and we'll cancel today's discussion session. How's that? It's getting to the time where you should be working on your term paper, right? So let's not have discussion session. Let's just take maybe 10 more minutes to go over a few points. One more slide left. Okay, finish this. Okay, what's left is to get an equation, right? Okay, I probably will not go through step by step. Maybe I will. About the equation. The equation is we eventually want to find out expression for this WCIB. We find out WCIB as function of JC, as function of the collector current density. We already see qualitatively now, the larger the current density, the steeper the slope, and therefore the larger WCIB. You see that? Right? So if the current density is smaller, the slope is smaller, and yet area is the same. Therefore, there's smaller WCIB, right? So just from this statement, do you agree that you should be able to derive an equation for WCIB as function of JC if you're given enough time? Do you agree? Right? What are the inputs that are known here? You know the area of these triangles, right? That's the applied bias between base and collector. Is that right? And you know the slope. Slope is given by this equation. Right? By this equation. You know the slope, right? Yeah? If you know the area, you know slope, you certainly know the base width of this, the width of the base of this triangle, right? Subtract the base of this triangle from your designed collector width, which is called the WC. The difference is your WCIB. Do you agree? So we'll not go through step by step. The point is that by doing it, you will be able to get a equation for WCIB as function of the JC. So we'll not go through derivation. You should be able to do that on your own. Okay? So the fact is that as we increase JC, WCIB increases, base gets wider, and therefore FT drops. All right? Okay? This whole thing is called the Kirk effect. It's also called the base push-out. It's also called the base widening. Okay? It's also called the base widening. And this is the thing that stand the way between us and the 100 gigahertz bipolar transistor. Actually, the best silicon germanium transistor has a FT very close to that, maybe 90 gigahertz or something like that, but you cannot use it for 90 gigahertz application. Of course, you cannot design all the way to FT. So if we did not have this problem, we could have 300 gigahertz transistor just by pushing to even higher current density. Cannot right now, right? Okay. Any questions about bipolar transistor? Okay, we have one more lecture to go about bipolar transistor. So let's just stop here right now, okay? Oh gosh, I did not turn on this, did I? Oh, you were able to still get it? Okay, good. They have a backup microphone, fortunately. So even when this